Welcome to Dr. Sherry's Astronomy channel. The topic of this episode is the ultra-fast gas bullets launched by supermassive black holes. The universe is thought to have begun about 13.8 billion years ago with a massive explosion known as the Big Bang. Shortly after that, the first stars were born. Over time, they came together to form galaxies. Even in those earliest days of the universe, black holes had likely already formed, either at the end of massive stars' lives or through processes that involved rapidly consuming surrounding matter. These black holes grew over time and eventually found their place at the centers of galaxies. Galaxies kept growing too, through repeated collisions and mergers with other galaxies. As this happened, the central black holes were also drawn together, merging and growing into even larger ones. Our Milky Way galaxy grew in the same way, through countless collisions and mergers with smaller galaxies. For example, this image shows the structure of the Milky Way based on data from the European Space Agency's Gaia satellite. Each component in this diagram is evidence that the Milky Way grew by colliding with and absorbing smaller galaxies. At the very center of our galaxy sits a supermassive black hole with a mass equivalent to 4 million suns. As the galaxy evolved, the black hole at its center changed as well, playing a key role in shaping the galaxy's growth. This close relationship is called coevolution, and it's a crucial concept in understanding how the universe came to be. When you hear the word black hole, you might picture a dark, heavy object that swallows everything around it. And that's mostly true, black holes don't emit any light, so we can't see them directly. But when gas or bits of stars get pulled in, everything changes. That material doesn't fall in right away, it spirals around, forming a swirling, disc-shaped structure called an accretion disk around the black hole. Inside this disk, matter collides violently, heats up to extreme temperatures, and shines brightly in X-rays and other high-energy light. That glow is how we're able to detect black holes from across the universe. One especially interesting fact is that black holes don't always consume everything they pull in. Some of that material gets blasted outward by a combination of gravity, pressure, and magnetic forces. This creates what we call jets and winds. Jets shoot out like narrow, focused beams and can travel tens of thousands of light years. Winds, on the other hand, are much broader and blow large amounts of gas outward in many directions. These outward forces can clear gas away from the black hole's surroundings or even shut down star formation, changing the way an entire galaxy evolves. But until now, we didn't really know how fast these winds blew, what shapes they took, or what structures they had. To truly understand them, we have to track how the gas flows, how fast it moves, and which direction it goes. We need to measure all these fine details with high precision. Unfortunately, earlier instruments just weren't up to the task. That all changed with XRISM, a new X-ray space telescope developed mainly by Japan. XRISM carries a super precise spectrometer called Resolve. This instrument can detect tiny differences in X-ray wavelengths, which allows scientists to measure gas motion in detail. Thanks to that, we can now study how fast different components of the wind are moving, what structures they form, and how much energy they carry. In March 2024, XRISM observed the supermassive black hole PDS 456, located around 2 billion light-years from Earth, and for the first time, revealed what's inside one of these cosmic winds. By analyzing X-rays emitted near the black hole, scientists were able to study the gas flowing through the wind. As shown on the left side of this diagram, intense X-rays are thought to come from a superhot layer of gas above the accretion disk, called the corona, and from the disk itself. These X-rays travel outward, passing through the gas in the wind on their way to Earth. As they do, some of the X-rays get absorbed by the gas, leaving clear fingerprints in the spectrum, called absorption lines. If the gas is moving at different speeds in different directions, it will absorb slightly different X-ray energies, so multiple absorption lines show up at different places in the spectrum. On the right side of the diagram, you can see real data with over 5 clear absorption lines. The horizontal axis shows X-ray energy, and the vertical axis shows brightness. In the top panel, the white dots are actual data, and the red line is the model. The deep dips are the absorption lines, places where the gas blocked some of the X-rays. Below that, 5 more panels labeled Zone 1 through Zone 5 show how gas at different speeds created each of those dips. The colored bands highlight which gas is responsible for which absorption line. From this, we now know that at least 5 separate gas bullets are being shot out of the black hole. These bullets are moving at 20% to 30% the speed of light, that's about 200 to 300 million kilometers per hour. Until now, we thought these winds were smooth and continuous. But XRISM's observations showed that the wind is actually made up of fragmented, intermittent bursts of gas, like bullets fired over time. XRISM didn't just detect the wind structure, it also captured light emitted by the wind itself, known as emission lines. Gas in the wind doesn't just absorb X-rays, it can also shine in X-ray light. This glow helps reveal how the gas is moving and how much of it there is. As shown on the left, the wind is blasting out from the black hole in all directions. Some gas is moving toward us, some away from us. Because of the Doppler effect, gas coming toward us looks blue shifted, higher energy, while gas moving away looks red shifted, lower energy. That's why the emission line spreads out instead of appearing as a narrow spike. On the right, you can see the actual data. The white line is the observation, and the red line is the model. The dotted blue and pink lines represent light from gas moving in different directions, toward us and away from us. They overlap to create the white glow in the center. This strong emission tells us there's a lot of gas in the wind. And because we see this emission from all directions, it shows the wind is blowing almost everywhere, not just in one narrow beam. Now that we know the wind structure is so different from what we expected, the next big question is, how powerful is it? The research team used XRISM's data to calculate how much gas and energy these gas bullets carry. They found that in just 1 year, the wind blasts away gas equal to 60 to 300 times the mass of the Sun. And this all happens within just 0.1 light years of the black hole, a very small area. Even so, the energy in this wind is over 1,000 times greater than winds that stretch across entire galaxies. Previously, scientists thought winds generated near black holes would spread out and impact the whole galaxy, affecting star formation and growth. But this new data suggests much of that energy might not travel that far after all. All this suggests that black hole winds aren't firing non-stop, they're more like bursts, launching at intervals and shooting out through gaps in the surrounding gas. This discovery challenges the old idea of coevolution between black holes and galaxies. To understand what's really going on, we'll need new models, new ways to think about how the universe works. By observing more black holes with XRISM, scientists hope to learn even more about how these winds influence galaxy growth. There's a lot more to discover, and the future of this research looks really exciting. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.